Hello ladies and gentlemen, welcome back for another Pytorch video. In this video we want to challenge ourselves and implement ResNet architecture from scratch. So this might be a bit more difficult than the previous architectures that we've done, but let's go through it step by step. First of all, let's look at some of the ideas from the paper and the general overview. The ResNet model won the ImageNet classification competition in 2015. And the general idea of the model is that when training deep neural networks, the accuracy should always go down as we increase the depth of the network, which in theory holds true, but since it can learn more complex features or mappings, but in practice it actually becomes worse after some layers. And this is the problem that the ResNet architecture wants to solve. Here we can see kind of an image of the ResNet architecture, in this case a specific one, ResNet 34. So to the left of it we see a 34 layer plane, which is just a normal, I guess, conv layer. This is just, we're going to take, so the next layer is just based on the previous one computed. And then if we look to the right, we see that there's some weird connection in between. This is what we're going to call a skip connection. So we see that for a particular layer, the one that I'm right here, it takes as input from the one before, right? The one that it previously computed, but it also takes as input what it computed a couple layers ago, in this case 2 layers ago. But as we'll see, the ResNet 50 and 100 and 152, it's actually going to be 3 layers in between. So in this case it's 2 in between, but the one we're going to implement, it's going to be 3 layers in between. Either way, the way here this works is that, so it can learn more complex things in these 2 layers, but it can learn new, more complex features, but it's also going to take this, what we're going to call the skip connection, the identity mapping from what it previously computed. So the network can kind of choose what it wants to have, either a combination of what it has learned and also this identity mapping, so that it can remember what it learned before. And the argument here is that, well, it can learn new things, but it's at least never going to forget what it learned before. So in theory, it should never become worse as we increase the depth of the network. And in fact, that's exactly what the ResNet shows. As we increase the depth, it almost never, I don't believe it ever worsens the performance. Here are the sort of implementation details that we're gonna focus on for this video, and we're particularly gonna focus on the ResNet 50, ResNet 101, and 152. And first of all, we can see that in the beginning it does a convolution with 7x7. So the 7x7 here is the kernel size, and then it's the number of channels and the stride. And then it does a max pooling. And yeah, so for the 7x7 kernel, it doesn't say the padding, but given the output size, we can infer that the padding should be 3. And yeah, then what it does is it has these, in this case, it has 4 different, what we're going to call ResNet layers. So if we're looking at the first ResNet layer, it has a block here, which is, first it's a 1x1 kernel, and then the second value is the number of channels, in this case 64, and it performs this this block 3 times. So it's going to do 3 3x3 kernels. So in this ResNet layers there are 9 conv layers. For example, in the second ResNet layer, it's going to be 12 convolutional layers, and the ResNet 50 is just if we sum all of those, the conv layers in this case, as well with the last fully connected, that's where we get the number 50 from. And one thing to keep in mind here is that if we look at the output size from this one, it's going to be 56, and essentially all of these are what we're gonna is same convolutions, meaning that none of them change the size of the input. But looking at the second ResNet layer, we can see that it's decreased the output size from 56 to 28, so it's half the size of the input. And then we can infer that the stride of one of these 3x3 kernels should be 2. And similarly, we can see that for the ResNet layer 3 and ResNet layer 4, it has also decreased the input by half. And one more thing to note is that if we look at the input channels here for the first ResNet layer, it's 64, and then the output at the end, the number of channels at the end of the first ResNet layer is 256. For ResNet layer 2, it's 128, and in the end, it's 512. ResNet layer 3, 256 to 1024. And so it follows the pattern that the input channels, if it's 64, 128, 256, it's always going to be 4 times the input channels at the end of that particular ResNet layer. So you can sort of see it that as the number of channels gets an expansion by 4 times the original. That's sort of the overview of the ResNet architecture. If you want to go and look at the more specifics, then I recommend you read the paper. I'm going to link it in the description. But now let's go back to the code. So the ResNet architecture uses these blocks multiple times in a ResNet layer. So a good idea might be to first start with creating the block and then try to build the ResNet architecture. So we're going to do class block. And yeah, I just want to say that this code is, for me at least, was a bit trickier than the previous architectures, and the code is kind of complicated. I'll try to go through it step by step so that we understand it. And the first thing we're going to do is the block that we're going to utilize later on. So all of these variables might not be very clear yet, but we're going to talk about them in more detail as we go on. So we're going to send in the initialization is going to take in channels and the out channels. And then it's also going to take some identity downsample, which we're going to set to default none, and stride, which we're going to set to default 1. So remember, the identity downsample in this case is going to be a conv layer, which we might need to do depending on if we've changed the input size or if we've changed the number of channels. So we need to adapt the identity so that we can add it later on when we've done a few conv layers. First of all, we're going to do super block self init. So we're going to call super, and we're going to do self.expansion equals 4. So remember, the number of channels after a block is always 4 times what it was when it entered. So we're going to first do self-con1, com2d with in channels and out channels. And then the kernel size will be 1, the stride is going to be 1, the padding is going to be 0. In between the next conv layer, we're going to have a batch norm with out channels. And then we're going to have essentially the same thing. I'm going to copy those 2 lines. We're going to do conv2 batch 2, and then we're going to do here stride is stride. Padding is going to be 1. Remember, the stride here is what we're going to input to the init, and the kernel is going to be 3. And so we're going to have the same number of, so out channels will be the number of in channels, kind of confusing, and then out channels will be the out channels. So it's just going to have the same number of channels. Then we're going to do another conv, and then conv2d with out channels. And then the output from this one is going to be out channels times self.expansion. So it's going to be 4 times the number of channels. And then the kernel size is going to be 3. Kernel size is going to be 1. Stride is going to be 1. Padding is going to be 0. And then lastly, another batch norm with out channels times 4 or self.expansion. We're also going to define a relu layer. Relu. And we're going to do self.identity downsample, and we're just going to call it identity downsample. And again, this will be a conv layer that we're going to do to the identity mapping so that it's of the same shape later on in the layers. So we're going to do define forward. And we're going to first say identity equals X. And then we're going to do a few computations. So we're going to go through each layer that we've defined. So X is self.com1. X is self.batchnorm1 of X. Yeah, and similarly for the rest, I'm going to copy in these values here. So essentially, conv batchnorm relu, conv batchnorm relu, conv batchnorm. And here at the end of those three, we're going to do, so after a block, that's when we're going to add the identity. So if self.identity downsample is not none, so we use the identity downsample layer if we need to change the shape in some way. So if it's not none, then we're going to run it through this identity downsample, and that's going to be our identity. Then we're going to do X plus equals identity and X equals self.relu of X. And then we're just going to return X. Okay, this is the block that we're going to reuse multiple times later on in our ResNet implementation. So now we're ready to move on to the ResNet. And then inherit from NN module, we're going to define init. And here we're going to send in first block, which in this, so it's just going to be this class. I'm actually not sure, we might not even have to send this in, but let's just do it in this case. And then we're going to send in layers and image channels and the number of classes. And the first thing we're going to do is call super ResNet and init. Yeah, so the block here is, as we said, it's going to be this class. Layers in this case is going to be a list, which is going to tell us how many times we want to reuse, or rather we want to use this block right here. So for example, I think in our case, if we look at the ResNet 50, I think it was 3, 4, 6, actually let me check. Yeah, 3, 4, 6, 3. So essentially we're going to use in the first ResNet layer, we're going to use the block 3 times, and in the second ResNet layer, the block 4 times, etc. The image channels is just the number of channels of the input. So I mean, either we have normally RGB, so we have 3 input channels, or if we have like MNIST, we would have 1 image channel. So we just have this to be able to make our ResNet implementation general in the way that we can input any type of images. Yeah, and the number of classes depending on what we have in the data. So first, we're just going to do in channels is 64. And we're going to do self.com1 is nncom2d. Image channels 64 output. That's always going to be the case. Then we're going to do kernel size 7, stride of 2, padding of 3. So this is just the initial layers. We haven't done any ResNet layers yet. And then just a batch norm. And then a relu. And remember also, we're only initializing the modules. We haven't actually called anything yet. So here we just in the init, we just define the layers, and then we're going to use them later on. And then we want a max pool. Max pool to the stride is going to be 2, padding is going to be 1. And then here we're going to do the ResNet layers. So we're going to do self.layer1 equals self.layer2. But to be able to make this simple, we're gonna call another function that we're gonna do to define make layer. And so this is gonna create the layer. So we're gonna send in the number of times it's gonna use the block, right? And then we want to send in like how many out channels it should be after that one. Yeah, so let's do just the input for this first. We're gonna send in block again, and the block meaning the class we defined first. Then we're gonna send in number of residual blocks. That's just what we're gonna call it. That's the number of times it's gonna use the blocks. And then we're gonna do out channels, which is the number of channels it's gonna be when we're done with that layer. And then we're gonna send in a stride. Because as we saw previously, so there's gonna be one of those, in this case, 4 times that we call the block. One of those is gonna have a stride of 2. And similarly for this one and this one. Except for the first one, it's gonna have a stride of 1. So what we're gonna do is we're gonna send in a stride that's either gonna be 1 or 2. First, we're gonna do identity downsample is none, and then we're gonna define layers to just be empty, and we're gonna add the layers as we go on. And then the first thing is that, well, we want to know when are we actually going to do a identity downsample in this case. Like when are we gonna have the conv layer to change the identity? Well, either we change the input size, so we have the input size, right? If the stride is 2, then we're gonna, for example, if we have 56 or yeah, like make it easy, 28 by 28, it's gonna be 14 by 14. Then we need to change that identity. So if the stride is not 1, or if self.inChannels is not equal to outChannels times 4. Yeah, so this is gonna make more sense later on, but if we've changed the number of channels, so if we have multiplied number of channels by 4, but the identity still has 1, so a quarter of what it has in the future, then we're gonna have to change the number of channels so that it can be added like we did here, right? So then if that's the case, then we're gonna do identity downsample is nn.sequential nn-comp2d, and it's gonna be out channels times 4. And since we only want to change the kernel, the channels, we're not gonna do anything different with the kernel. We're just gonna do a kernel size of 1, and then the stride will just be stride. Then, so let's see. Then we're gonna do just a batch norm. And that's it for the identity downsample. And so let's see now. What we want to do also is then we're gonna do layers.append. And what we're gonna do in the first one is that we're gonna change the number of channels. So this is a tricky part. The in channels is just self.inChannels, and then we're gonna do out channels, which is gonna be, so we send in the out channels right here. So for example, I think in the first case it's gonna be 64 input channels and the output will be 256. And then we're gonna do identity downsample that we just created with that specific stride. So essentially, this is the layer that changes the number of channels. So after this block, which is the first block that we append to layers, is gonna change the number of channels. In this case, if we look at the first ResNet layer, it's gonna change it to 256. Then what we're gonna do is we're gonna update self.inChannels to be out channels times 4. Yeah, sorry. So I think I did a mistake. So the out channels in this case is going to be 64. But remember, as we define the block, it's going to be, the output from this is going to be out channels times 4. So it's going to be 256. Just that out channels in this case is not going to be 256. It's going to be, it's going to be 64, but it's going to be multiplied by 4 in the block. So it's going to be 256 at the end of this block right here. So that means that we need to change the number of in channels. The in channels is now going to be 256. So it's going to be, in this case, 64 times 4. Then we're going to do for I in range of the number of residual blocks that we're going to compute in this case, minus 1. Because we computed already one residual block right here that changed the number of channels. And then we're just going to do layers.append block self.in channels and out channels. And then in the end, we're going to return nn.sequential of layers. So this will unpack the list, and it will do so that Pytorch knows that each of them will come after each other. So I think I want to add a few comments, because literally these are the most difficult parts of the implementation, I believe. So first of all, here the number of in channels in this case is going to be 256, and the out channels is going to be 64. So in the end of the first block that we did here, the output is going to be 256, but the out channels in this case is 64, right? Because we need to map 256 back to 64, and then in the end of that block, it's going to be, output is going to be 64 times 4. So it's going to be 256 again. So essentially it's going to be input 256, and then it's going to map it to 256 again, going through intermediate conv layers where it goes from 256 to 64 and then back to 256. And the stride in all of those cases is going to be 1, and the number of channels is the same, right? 256 is the same number of channels. So we're not going to use the identity downsample in this case. The only case where we change the number of, the number of channels and the stride, so the input, is in this first block. Then the other ones are going to be stride 1 as we define as default. So this means that we're just going to do this one without doing the identity downsample. That's only for the first block. Yeah, and then we can just do this loop, and in the absolute end of the loop, it's still going to be 256 output. Yeah, all right. So then what we want to do is, now we're ready to define the ResNet layers. And then we're going to do self.makeLayer. We're going to send in block, meaning the class that we defined. We're going to send in layers 0. So in this case, yeah, this layer 0 is going to be this list here. It's just going to be the 3. Actually remove this. And then out channels from this is going to be 64. And remember, it's going to be the out channels. So the name is a little bit confusing. It's out channels times 4 at the end. Yeah, and then we're going to do a stride of 1 for the first ResNet layer. Then let's copy this and use the layer 2 and change this to 1. And then in the out channel, it's going to be 128. And then in the end, it's going to be 128 times 4. And then for the rest layers, we're going to use a stride of 2. So let's again copy this, layer 3. We're going to do block and layers 2. And here's going to be 256. Again, stride of 2. And then for the fourth ResNet layer, it's layers 3, and the out channels is going to be 512. So 512 times 4, it's going to be 2048 channels at the end. And again, a stride of 2. Then we're going to do self.averagePool. And we're going to use nn.adaptive average pool, which essentially is that we define the output size, and it kind of does an average pool that, depending on the input, that's going to fix it to that particular size. In this case, we want a 1 by 1 at the end. And then we're going to do a fully connected layer at the end, which is going to be 512 times 4, right? So the number of channels here times the expansion, which is 4. And then we're just going to map it to the number of classes. All right. And then what we're going to do is one more thing. We're just going to do forward on all of those. So x is self.com1 of x, self.batchnorm1 of x, and then relu, and max pool. And then we're ready to send in through the ResNet layers. So layer 1. And I think just for a moment, like, appreciate how much goes into that particular layer. We're calling the make layer, which calls the block multiple times, and the block by itself does a lot of like 3 conv layers. So there's a lot to unpack in just one line that we're gonna do in the forward. And then layer 3 of x, 4, and then we're gonna send it through the average pooling to make sure it's of the correct shape, or yeah, to make it output 1 by 1. And then we're gonna reshape it so that it's we can send it into the fully connected layer, and then self of fully connected of x, and then we're just gonna return x. Okay, now what we want to do is we want to define ResNet 50, which is going to take as input number of in channels. Yeah, so we're going to do im channels, and let's say number of classes, which we're going to set the default to 1000, and also im channels 3. And then what we're going to do, we're going to return ResNet block, and then the number, so the layers 3, 4, 6, 3 in this case, and then we're going to do im channel and the number of classes. And really, so all that we need for the ResNet is this one, right? That's what defines the ResNet 50. So we can do the same thing for the rest, for ResNet 101. Except all we're going to do is we're going to change this. In this case, this the 6 becomes 23. And again, so really now we notice that there's not that much difference between the different ResNets, except that they're larger. So here we're going to actually change this to 8, and we're going to change this to 36. And then to test that we've actually implemented it in the right way, we're going to define test. We're going to do x is torch.random, and we're going to do, let's say we have 3 or let's say we have 2 images, just to make it fast. Normally this would be 16 or 32 or 64 or something like that. But yeah, this network is quite expensive to run, so let's just do 2 and let's do 3 to 24 to 24. So the number of in channels in this case is 3. And then we're gonna do y equals net of x, and then let's do 2 CUDA. So we're gonna let's see, we need to do net equals ResNet 50, ResNet 50. So we've defined the network, which in this is ResNet 50. We have some random input just to check that the shapes are correct. Then we call the net, and then we're gonna do print y.shape. And finally, let's call test. So this is the moment of truth. Let's see if all the implementation we've done actually works. Bring up the interactive Python. Let's run this. Damn it. Okay, so im channels. Yeah, this should be im channels. Okay, let's run it again. Channel. Yeah, so this is out channel. It should be out channels. All right, and perfect. It works. So let's actually try all of them. Let's just see that they do the right thing. And ResNet of 152. All right, that's great. this code is, I sat for a couple of hours just to really understand the code, and it's kind of difficult to understand all the steps. Hopefully this was useful, and if you have any questions, then leave them in a comment, and thank you so much for watching the video.